This is the screen you should see when you first open BuzzerSonic. There will be slight differences depending on the type of hardware you've got installed and on the various add-ons that you may have purchased. But it should look essentially like this. And what I'm going to do is just walk you through testing a couple of three samples today. And we can describe the interface as we go along. But just to give you a little brief overview, on the left hand side here is the sample database. This is where you will store and retrieve all the testing data for the samples that you test. On the bottom here are the various shapes that we can test, the various modes of vibration that we can test. On the bottom here, left hand corner, is related to the sound input device attached to the computer. Along here are the controls for the waveform and the spectrum. And here is the main table showing the results. It's like a spreadsheet. It shows it displays the results of the testing. And these are just controls to show and hide various aspects of the table. These are the units that are being used. This is for exporting to Excel, and this is for looking at different getting frequency estimates. But we'll describe that later. So on the main table, elastic constants panel, there are other ones available, but this is the one you should select, and it's the one that's selected automatically. Okay, so we'll start by testing an aluminum standard. Now if you have the aluminum standard that we supplied, you should install the test data that comes with it, and that will be displayed here under the category. This is a category standards. And underneath that are the different groups of data associated with that category. So this was tested at our Buzzmark site, so that's just called Buzzmark. And here are the groups of samples in the data table. As you can see, we've only tested one sample here, so there's only really one sample associated with this group, and that's the aluminum standard. But as you can see, we can retrieve the information, the waveform, amplitude versus time, and the spectrum, power or amplitude versus frequency. So now we'll test our own data, which is the default is called user data, that category. You can change that to anything you like, so let us change that today to, let's say, demo category. Now the group is, by default, it just numbers it 1, 2, 3, 4, etc. We can change that name as well if we want. So I'm going to call that demo group. Like I say, it can be anything you like. Now we're going to test an aluminum bar. Oh, I can spell. So you type it in, then you can tab to the next field. So if you look at this table, it's split into two parts. On the left hand side are the physical properties, and on the right hand side are the measurements taken by BuzzerSonic, and then the calculations, the Young's modulus, She modulus, Poisson's ratio, sound velocities. All that information is displayed in this part of the table. So here we're going to start putting in the dimensions, the mass, the density, the Poisson's ratio, anything that is required by BuzzerSonic to do the calculations. The first thing we need to do though is make sure we've got the right unit selected for the dimensions, mass and density, and that is selected here next to this little physical property or micrometer indicator. At the moment we're on metric. You can have SI, English, you can have different units, mixed units, but here for example we can have centimeters for length, grams for mass, and grams per cubic centimeter for density. But we'll leave that on metric. Here are the units for the Young's modulus, given the symbol E, or elastic modulus E, and She modulus G. At the moment they're on SI units, but you've got metric, English, and then you've got various combinations, because BuzzerSonic also measures sound velocity. For example, here we've got kilopounds per square inch for the Young's modulus and She modulus, and feet per square second for the sound velocity. So we'll stick with SI here for the demo. So now we can start putting the dimensions of the sample that we're going to test. Well, one thing usually when you put in the dimensions, you usually use an average value or a mean value. So we can do that under BuzzerSonic, just right click and then put insert mean. So it tells us we're looking at length here, and now we can just type in the dimensions. Type them in, then press the enter or tab key to go to the next row. Now we also display those dimensions here, and that's a good indicator of whether you've got reasonable values. So if you accidentally mistype, you can see straight away that there's a mistake there. So this helps eliminate human error, or operator error. We also get a standard deviation, so we can tell whether we've taken enough measurements to get a reasonable value of length. Once we're satisfied, we could click the OK button, and then that would send that mean value of 304.77 to this length cell here. But because we're going to do the width and height as well, take mean values, I don't want to close this window, so I can just say send that information, send it to the table. So it stays open, so now we just simply click on the width column and we can now enter in the width. It's a floating window, so it doesn't close or go behind the spreadsheet or the table. And we'll just type in a few values here. And we do the same thing again, and same for the height. Like that. Now we can close it, we can enter it and close it at the same time. Now here we have a choice. Because BuzzerSonic needs to know the dimensions and the density of the sample, we can enter in the value of the mass, and then BuzzerSonic will do the density calculation knowing the mass and the dimensions. But if we know the density, we can just type that in directly. If you just press tab, you could enter a value here. In this case though, I'm going to just enter in the value of mass, and then BuzzerSonic will calculate the density. So what I will do is press the tab key twice. That way I don't enter anything into the density column, and BuzzerSonic will realise that and then do the calculations. Now in order to measure the Young's modulus for a rectangular bar that we're testing in this case, to get precise measurements we need to know what the Poisson's ratio is. Now we can calculate the Poisson's ratio using two different modes of vibration, but what I do, or what I recommend, is when you're doing this test, is to put in a placeholder value for Poisson's ratio, just so that BuzzerSonic can go ahead and calculate the Young's modulus. It's only a weak dependency on Poisson's ratio anyway, so we only need to put in an approximate value or an estimate, and that way we know we're getting a good frequency measurement when we get the Young's modulus. So for metals we put in 0.3, for ceramics 0.24, and for polymers 0.4. But like I say, it's only a placeholder. It doesn't really matter that much. As long as you put something in there, BuzzerSonic will then calculate the Young's modulus, and then we know that we're getting reasonable values when we're doing the test. And I explain how we can get BuzzerSonic to calculate the real Young's modulus later. Alright, so the next thing we need to do is set up the sample to do the testing. As you may recall, if you look at this little diagram down here, you see that to do this particular mode of vibration, outer plane flexure, we need to put the sample on two parallel knife edges placed at 0.224 of the length from each end, or have a knife edge span of 0.552. So let us set up the supports to do that. Now we know what the length is, so if we multiply 304.77 times 0.552, we'll know what the knife edge span should be. But rather than let's do the calculations, we can let BuzzerSonic do it. So we go to testing info, and here we can tell BuzzerSonic, here BuzzerSonic will tell us what the knife edge span is, 168.2. So let us set up that. So I'm setting my calipers to my micrometers to 168.2. So we'll set those to 168.2. I've always set up the knife edge span, but you would set the width here. Make sure these wires are at 168.2 across. Now we're going to centre by eye. We'll move this out of the way. Now we're going to centre this on the wires, on the supports. It's okay to do this by eye, it's close enough. And then we bring the microphone over the antinode, which the antinodes are either this end, or in the centre, so the microphone can go there, there, or there. And then we would excite this sample in one of the other antinodes. Now we're going to use the standard impulse tool. Is this according to ASTM E1876 and C1259. This is the standard impulse tool. It's light, it's hard, and it gives a very wide range of frequencies because it doesn't contact the sample for very long. The longer the impulse tool is in contact with the sample, the lower the narrower the frequency range input into the sample. So if we want a wide frequency range, we'd use a tool like this. But because I know this particular sample has a relatively low frequency, I can use our xylophone mallet, the ME101. I know this works really well for this particular sample. It's a little heavier and softer than the standard impulse tool, and therefore it puts all the energy into the lower frequencies, which is what we want in this case. So going back to the Buzzosonic here, because I'm going to use the ME101, I'll put that into the testing information. You can put other things in there, of course, my initials. If you want, you can put information here, anything you like, and then that information will be stored with this particular mode of vibration and this particular sample. So we can close that now. Now we need to make sure that when I hit the sample or strike the sample, there's enough sound volume to go past this little slider. So what's happening here, this is the sound coming into this USB 6210. So let me just describe this sound input a little bit. This will show the different cards or data acquisition cards or dynamic signal analyzer cards that you have attached to the computer. Now this list is actually made when Buzzosonic first opens. So if you attach your device after Buzzosonic opens, you would click this little event button and it resets this list. Also, if for some reason one of these devices stops working, you can reset the device with this little event button. So here we select the data acquisition card we want to use. If you have the USB 6210 attached, it will be selected by default, or if we've provided you with other sound cards, they are usually selected by default. So make sure that's selected. This here is for the different systems: room temperature, high temperature, cryogenic. We're testing at room temperature, so we'll leave that on room temperature. This is the sound coming in through the USB 6210. So when I tap the sample, you can see that we're selecting the sound. You will also notice that the sound volume is indicated here. And when that sound volume exceeds wherever this little triangle is, we can threshold slider, we can move that around, we can shift that. But for now I'll leave it where it is. When that sound volume exceeds that lets Buzzosonic know that the sample has been hit. But we also want to let Buzzosonic know when we're going to do a test, and that's what this button is for. When it's activated, we're telling Buzzosonic we're about to do a test. You can use the mouse or you can use the spacebar. So let me use the spacebar and do this test again. Oh, one more thing we need to do. And we're going to make sure that we've got this is the resolution here. We should set that to 1, that's the highest resolution. We can try different resolutions once we've done the first test, but let's just do the first test at 1 at the best resolution. Because Buzzosonic uses a fast Fourier transform, it actually, well, to explain this a little better, where the resolution is determined by how long you measure the sound for. So the longer you measure the sound, the higher the resolution. 1 second of sound will give you 1 Hertz, 0.1 second of sound will only give you 10 Hertz resolution, and so on. And also, so But to satisfy the fast Fourier transform conditions, Buzzasonic actually captures more sound than just satisfies the resolution. So we actually end up with a higher resolution than we select here. So when we say we want 1 Hertz, we end up with 0.95. If we select 10 Hertz, we end up with 7.6. So we always get a better resolution than we request. And also Buzzasonic actually captures more sound so that we can offset the waveform from the initial conditions, because when you first hit the sample there are transients which can sometimes interfere with the test, and you can get better analysis by offsetting it slightly. We'll describe that in a second, but for now set that on 1. These window functions, we don't need to go too much into these, but leave that on square. That just means there's no window function applied to the waveform. Power refers to the amplitude that's used in the frequency spectrum. Power is the amplitude squared. That's the one we recommend. It gives you the cleanest spectrum. It eliminates any additional peaks that you don't really want. But you can actually use different settings. You can use amplitude or decibels. Leave that on power for now. So power square 1 is the best initial settings to use. Make sure this is on 0. This is the waveform offset. We'll describe that later. This is the USB 6210 gain. Minimum, low, medium, maximum. So leave that on medium. We know that's going to work okay anyway. So now we're ready to go. Press the space bar and hit the sample. Press the space bar again. Now you see what we have. We've got the frequency 1058. You may notice this little green threshold cursor. What this does is that any peak that's above this cursor will be labelled, and that labelled peak will then be displayed in this little table here. So this table really summarises the data we've just got. It tells us that we've got one peak labelled, and that peak is 1058 Hertz. The power on this axis here is 1.42. The internal friction, measured by the logarithmic decrement method, is not shown. I'll explain why in a second. I'll explain what these mean in a second. This is the internal friction calculated from the width of the peak in the spectrum. It's called the half-peak broadband method. It's fairly inaccurate, as you can see, 190.6% plus or minus, so it's almost 200% plus or minus. The reason for that is because it only really works for heavily damped materials. So this is only really useful if you have heavily damped materials. In this case, it's lightly damped, as you can see. The waveform goes on for a long time, and you see the transient here, how it decays quickly, then settles down. So that is why we don't get a good internal friction measurement. What we want to do, what Buzzatronic tries to do, is fit an exponential decay curve to the waveform envelope. That's the logarithmic or decrement method. So it's fitting a curve to this waveform envelope. It can't fit the curve because it's changing too quickly here. So what we can do, if you want to get the internal friction, is to offset it slightly. So when we offset it, we see now we can get a good fit to that curve. So now we get a value of internal friction, this q to the minus 1. This mean squared error tells us how well this fits. As long as it's below 1, it's usually pretty good. And then this is, like I say, is the estimate from the half-peak broadband method. It's like I say, it's not accurate in this case because we've got very light damping, so we can pretty much ignore that. So now if we want to get the Poisson's ratio and a good value of shear modulus, we would need to measure the torsional frequency. So now we're going to go to torsion. So let's set up for torsion. In this case, because this bar is so quick, we'd normally use the cross wires here. We use the cross wires, but this sample is actually too big for that. So what we're going to do is this is the automatic impulse tool. We'll just take this out for a second. It's in the way. We'll describe that later, but for now what we're going to do is put the 2 knife edges together to form one cross knife edge. one of the crosses on the knife edge. So we'll put these together for this particular sample because it's too large, and then we're going to put these at 90 degrees. So it's good enough to do by eye. We're going to center this sample on these wires on the cross, and then we're going to place this microphone approximately where the node for flexure would be, for the fundamental flexure. That way we eliminate the fundamental flexural frequency, or at least we reduce it, and then we just get the torsional frequency. So we put the microphone where the node for flexure would be, the fundamental node, and then we can excite the sample at these nodes as well. So let's go ahead, we're going to turn on the analyze button here. We've turned it on by pressing the space bar in this case, and then we'll do a test. And then we'll stop. Now, one thing I should have mentioned, we'll just go back to the outer plane flexure a second. And look, as you would notice, it will recall that data. When you first test a sample, once you've got the frequency, the outer plane flexure in this case, and you've got a Young's modulus that makes sense, oh yeah, that looks right, then you might say, well, what torsional frequency would I expect? And that's what this one's for. So if you click on this, you can now use this to give us an estimate of what the torsional frequency should be for this particular Poisson's ratio. And so here we've already got the Young's modulus calculated. This is another reason for putting a Poisson's ratio in. We can then calculate all the other frequencies we might expect, and these are the order of frequencies. So 1 is all fundamental, 2 would be the first overtone, second overtone, third overtone. Now it's useful to put these in sometimes in case you get an overtone close to where the torsion is, for example. But in this case, it's pretty clear. We can see the torsion, we would expect the torsional frequency to be around about 3000. Oh, by the way, you can also show these curves, well, I mean the expected frequency on the spectrum. If I go to the next line, you can see how we can identify. This is one good way of identifying peaks in the spectrum. Now if we don't want those on there, we can just turn them off there. So we know it's around about 3000, we can either OK or cancel it. So now we go to torsion, knowing now that it should be about 3000. We've already just measured it now, and yes, it is at 3000. So we know that's a good value, so we can now take away our placeholder, and here now we get the Poisson's ratio calculated here. Now just to go through some of these, you see at the moment we're not displaying the flexural frequency, we're just displaying the torsional frequency. The reason is these buttons here. Now these buttons are used to show and hide certain columns in these tables. So and also different elements. So for example, if you don't want the grid lines, you can turn that on or off. If you no longer want to display the physical properties, you can hide them. If you're not interested in doing high temperature testing, you don't need to put the thermal expansion coefficient in, you can hide that column. Now going across here, you can hide the frequency column, the power column. We'll leave those, well we don't need the power, we don't need this, this is the broadband internal friction, we don't need that. We're not interested in sound velocity. We're not interested in the sound velocity calculated by twice the length times the longitudinal frequency. That's used a lot in refractories. We want to show the Young's modulus, we want to show the Poisson's ratio. This is the flexural rigidity, it's just the Young's modulus times times the moment of inertia. So it's Young's modulus times the moment of inertia. It's useful in the paper industry, but it's not useful to us, so we can hide that. This column here is for grinding wheels where they have a hardness grade and it's given a letter like A, B, C, D, E, F, G, H, I, J, K and so on. So this is why that's got the letter K. We don't need that. So we've just got the ones we're interested in. We've got the grid lines, the physical properties, the frequency, the internal friction, the Young's modulus, the Poisson's ratio. Now this one here, these columns are then filtered on top of the ones you've selected. So by filter I mean, if I just click on the X, that just means I want to show only the columns that are pertinent to the mode of vibration under test. So in this case we're measuring torsion, so it will only show the torsional frequency. Now if I wanted to show the flexural frequency, if I click that, I will then get all the different frequencies that could be measured. So we get a lot more information. So sometimes it's just good to keep that one hidden, just to keep it simple. Now this one will show you the mean values. I like to keep that checked because then it also shows the Young's modulus as a mean value. So you can get a lot of information in one screen without overburdening the screen. So this shows the mean value, and then this shows the values pertinent to the mode of vibration. So if I go back to outer plane flexure, you'll see I'll get the flexural frequency and everything else. Now, the reason for using averages here, by the way, is because you could measure the internal friction from other modes of vibration. This is outer plane flexure, that's where the out comes in. This is the outer plane flexure, internal friction from outer plane flexure, but you could get it from in plane, from longitudinal, and then you could take an average. Of course, we've only measured one mode, and so we only get, we've also measured it from the torsional frequency, so we do get a different average here. Here we've got the outer plane flexure for Young's modulus. We've only measured Young's modulus from one mode. You can get it from in plane and longitudinal. So these two numbers match. We've got the shear modulus, and the Poisson's ratio in this case is determined from the outer plane flexure and torsion. So this just indicates it's always determined by the torsional frequency, but it can be determined from the outer plane flexure, in plane flexure and longitudinal frequencies, and that's why we have an indicator to say this one was determined from torsion and out of plane flexure. If you determine it by the in plane and longitudinal as well, we would have a different average value here. So that explains that. Okay, now let's go on and measure a ceramic bar. So I'll just call it ceramic number 1 in this case. I've already got the measurements. I'm not going to use mean values in this case, I'm just going to just type them in. We'll put 0.24 in this case because it's a ceramic. So once again we can go to the testing information. I'm going to use the standard impulse tool this time. The knife edge span is 57.5. So we'll adjust the knife edge span to 57.5. So we'll take the sample off. So we'll set it at 57.5. Center it. Move this out of the way. Center this on the wires. Bring the microphone over the node again, so it's just like we did last time, but this time we'll use the standard impulse tool. We're going to use the standard impulse tool. So once again we'll go 1 Hz resolution. We'll have rectangular bar, outer plane flexure, everything set up. So we'll press that now. Press the space bar. So we've got the value we want, 3138. Now we'll go and measure the torsion. In this case we're lucky, we can pretty much have it use across wires this time because the sample's small enough. We don't have to adjust it too much. Once again we put that under the node, press the space bar, press the space bar again. Now we can take out the 0.24 and there we have it. Now we could have gone through this check again like we did last time. So that is simply how you would measure that ceramic bar. Now let's go and change to doing a disc. Now I could just simply select disc and then put a different, let's see what happens when we do that. So now we've got another set of data, we can put that here, or if we want rather, go back to there a minute. We could actually insert another group here, so we want to insert a group. I'm going to call this demo group. But we don't need to do that, it's just to show you some of the other things you can do. This time we're going to do a disk. So we've got demo group 2, now I'm going to put in the sample data. I've already got the height and everything. So I'm just going to enter those in directly. We'll put in a placeholder again. So in this case we can put the sample on the cross wires. For the first mode of vibration, make sure the microphone is between these two at 45 degrees and on the edge. And we can use a space bar to turn the analyze button on and off, so we're going to turn that on. Make sure this is on, that's all the way down, the waveform offset's on 0, we have power, square, start on 1 Hz resolution, make sure these are all set the standard way, then we'll do a test. Press the space bar. Okay, so we see here, interestingly, that it decays very quickly. So we don't need all this, this is all wasted information. So we can go to a lower resolution if we want. But if we're interested in the internal friction measured by the half-peak broadband method, we should use a 1 Hz resolution. Now if you look here, because it's more heavily damped than the other samples we tested, we see now that these two methods of internal friction are starting to agree with each other. One derived from the log decrement method, or fitting the curve to the waveform, and the one derived to the half-peak broadband method, or the width of the peak in the spectrum. Those two methods are giving us similar results now, with a much lower error on this one. But if you go to a 10, if you're not interested in the internal friction or using the half-peak broadband method, we could easily go to a 10 Hz resolution instead. It'd be much quicker to do the test, and we're not really losing much information. So in this case, I would go to a 10 Hz resolution. Now let us see what we should expect. We've got a Young's modulus of 216. If you look here, we should expect the next mode to give us something like 21,000 or 20,000. So to go to mode 2, we would need to use the foam, a flat piece of foam, because we have to hit the sample in the center, and the easiest way to do that, the easiest way to support it is simply to use a flat piece of foam. So just to show you that we should get the same results as when we use the sample supports, if you look at the microphone there, I'm going to hit it at 90 degrees on the outside. So we should get something similar. Or before we do that, let me just explain one more thing. Here we've got the information we want. Now if I go to look at the next mode of vibration, you'll see that it automatically clears everything. If I go back to the one we've just tested, it retrieves that information. That has been stored automatically. So when I switch from one mode to the other, or from one sample to the other, if it's the first time I've tested the sample, that information is stored automatically. Now notice now what happens when I try and do a test. I'm going to test this sample. I didn't hit it very well. There we go, so I didn't hit it very well. But now if I can hit it properly, you see I get a very similar result. But look what happens when I go to the next mode and then come back again. It's retrieved the initial information, not the new information. That's because Buzzasonic will store the first set of information, or first data set, when you go from one mode to another or change samples, but it won't. To prevent it being accidentally overwrited, you now have to tell it if you want to change that data. So let's do this again. So I've got the new data. Now in order to, I've got two options. I can overwrite what I had last time by clicking this green button here. So let's do that. Well, actually, before we do that, let's do one more thing. We'll add this to the database here. So, to this, we can add this information to a set of statistics. So I'm going to add this new value. So now I've told BuzzerSonic to add it to the statistics. I've got two values. If I go back to this one, that retrieves the initial data set. And if I go to the new one, you see I'm getting similar results, a little different, but it's not really affecting. If you look at the Young's modulus, it doesn't really change the modulus. So I'm going to stick with, but then we can get the statistics here. So we get some statistics here. So now I'm going to go and test it for the next mode of vibration. This time I hit the sample in the center. We knew we should get 20,000. We did, or nearly 21,000. We can turn this off. So now we get rid of this. Now we get the actual Poisson's ratio. One other thing to show you here is, instead of turning this on and off each time, if I click this little one button, this is telling BuzzerSonic that when this threshold gets past this slider, then it will automatically turn this off. So let's see if that works. So there, turn it off so you don't have to keep turning this on and off. And of course this will determine what's in the table there, anything that's above this slider, if you've got more than one peak. This threshold will do that. You can use these to zoom around peaks. This zooms it out. But if you do zoom, you can then move this around with a hand, zoom out again, but always click this one so you're now ready to use this threshold slider. If you've got the threshold slider too high up, or you can right click and say center threshold. This of course you can offset like we showed you before, but if you want to reset it, just click that. Resets everything. One other thing to show then now is the automatic impulse tool. So let's go back to the other group here. We'll go back to the ceramic bar. As you may recall, the wires were set up for the ceramic bar, so we don't need to change anything there. Here's the automatic impulse tool. I'm going to place that over the tool. Now one thing to make sure is that this tool, if I press the solenoid and this is all the way up, the tip of the tool should be just a few millimeters from the bottom of the sample. When the solenoid's all the way up and this is its highest level, it should be just a few millimeters from the surface of the sample. So then we center it over the sample like so. Now we're going to use the automatic impulse tool. That's this one here. If you've got this attached, you will need to put some value here. This is the power that goes to the impulse tool. So let's try a value of, say, it's just volts times amps. Let's try 3.8. Not enough power, so let's try, just type it in. I'm going to type in 6. Now I can bring this down a little bit. So we see that would go past there. Now what we can do here, I didn't put the microphone over the sample. It's a good idea to put the microphone over the sample, that's probably why. So we can either click this, or we can press the F2 key. So I'm pressing the F2 key. Notice that this one automatically turns off the analyze button. We see that we get a similar value to what we had before. Let me add this to the database just to show you. So if I go to the one we did by hand. Oh, sorry, it was in torsion. Oh well, I did the wrong. I forgot to set this to flexure. So this is okay, because now I'll show you. We can delete that. We've got it in the wrong one. I should have set that to outer plane flexure. No problem. So what I'm going to do now is press the F2 key. Now I'm going to add that to the sample statistics. Now you see that I get a very similar value to what we had before. Just a different bit of a waveform, but it's very similar. Well, it's the same frequency.